Now in today's episode of 12 integrals, we're not going to be looking at any particularly interesting integrals. But what we're going to be doing is we're going to be looking at what we could do with integration and how we could apply it to something else in mathematics. Before I get into my question today, I'm going to talk to you guys about two different words: convergence and divergence. So let's say I have a sequence, 1 plus a half plus a quarter plus an eighth. You sort of see the trend here, right? If I add up each of the terms one by one, then you could see that the sum actually tends towards a particular number. The sum actually seems to tend towards 2. As you add more and more numbers, the total sum seems to slow down and approach a particular number. When this sum actually approaches a particular number, we call this a convergence series. So this series here is actually convergence because the sum tends towards 2. And the opposite of convergence series are divergent series. An example of it would be something like this: 1 plus 2 plus 4 plus 8. As you add each of the numbers, the sum gets bigger and bigger and doesn't actually seem to slow down at all. And the sum actually tends towards infinity, which means that there's no limit for the sum, hence a divergent series. And so now that you know what convergence and divergence is, let's get into today's question. This is called the harmonic series. It's just adding these particular fractions together. 1 divided by 1 plus 1 divided by 2 plus 1 divided by 3, so on until infinity. What I want you to do is to find whether this series is divergent or convergent. So I'll give you a bit of time to have a think about it. You can write stuff on a piece of paper. Do you think you have an answer? Alright, so let's see how we could do this using integration. Now there's more than one ways to show whether this series is convergent or divergent. But what I'm going to be using today to prove the convergence or divergence of this series is something called the integral test. So if you've done calculus before and you know what the integral test is, you can just close this video now. But for those of you who's not familiar with the integral test, keep watching. Now this is what the integral test says. Let's say you have an infinite sum that looks like this. Well, what you can then write out is you can write out an integral which looks like this. It will be integrating over the same function as the sum, and the limits will be the same as what it is in the sum. And interestingly, the behaviors of these two expressions will be the same. In other words, if the sum is divergent, then the integral will also be divergent. In other words, the integral will tend towards infinity. And if the sum is convergent, then the integral will also be convergent. In other words, the integral will actually tend towards a particular number. And if you stop and think about this geometrically, it does in fact make sense. Let's consider this. This is the graph of f of n, which is the graph that defines each of the terms in your series. Now I can draw rectangles that look like this. The height of each rectangle will equal to how much each term is, and its width would just be 1. So if you add the areas of all these rectangles, you will just get the sum of the infinite sum that you're interested in. And you can compare this to the area under the graph, which is this area, and that is just the integral of the function. And so as you can see, the area under the graph and the area of the rectangle is somewhat approximately going to be the same. And so then it would make somewhat of sense that if the area under the graph tends towards infinity, then the areas of the rectangles added together should also sort of tend towards infinity. Now I know this isn't the really rigorous mathematical proof for the integral test, but this is just how you can think about why the integral test actually even works in the first place. And so now we can just use the integral test on the harmonic series, which is what I asked earlier. So let's bring up the harmonic series again. Now the nth term of the harmonic series is 1 over n. So f of x for this case would be 1 over n. And so what we can do now is we could just integrate 1 over n with respect to n, going from 1 all the way to infinity. And this integral is pretty standard integral that you should probably already know. It comes out to natural log of n, and then if you evaluate the limit, it will go to infinity. And because this integral goes to infinity, it means that the harmonic series also tends towards infinity, and hence harmonic series is a divergent series. And so yes, that's it for the third day of 12 integrals. Hope you enjoyed it, and I'll see you again tomorrow. Goodbye.